Hello all, welcome to the next lecture of electromagnetic theory and transmission lines. So till now we have discussed the various concepts related to electromagnetic theory. From this lecture onwards, we will be discussing about the transmission lines. So the transmission lines basically are, as the name indicates, the first topic in this is about the introduction to transmission lines. So as the name indicates, the transmission lines are basically a medium, a medium that is used for transmitting electromagnetic waves from one end or from load or source to the load. Okay, so these are the transmission line is basically a media, right? It is basically a media that is used for transmitting signals from the source to load or from one system to the other system. Okay, so these are used for transmitting electromagnetic waves, EM waves. Okay, so the signals that carry electromagnetic energy, right? Whatever the waves that we have discussed till now, right? These waves, okay, they can be used to propagate, or they can be sent from one system to the other system using a bounded media. So here, those the media that is required for transmitting the electromagnetic waves are the transmission lines. Okay, so right, the transmission line is a bounded media by which we can transmit the electromagnetic waves from one end to the other end, or from one system to the other system. So transmission lines has, what does a transmission line have? So a transmission line has a pair of conducting wires separated by a dielectric media. So this system, it is a system which has two parallel conducting wires, right? This should be coaxial or parallel to each other. So two parallel conducting wires separated by a dielectric medium make up the transmission line system. So transmission line can be formed with the help of this structure. So here, the dielectric media that we are going to use, it can be either air medium, or it can be any other media such as paper, etc. And generally we use copper or aluminum to construct the conducting plates. Okay, so this is the general structure of a transmission line. Now here the biggest question that we should get is, so in general, whatever the electrical wires that we use, right, those wires, okay, or the connectors that we use in our systems, they also, right, have two conducting wires, right, separated by shielding or separated by dielectric. So what's the difference, right, between those wires and a transmission line? Why are we discussing this transmission line separately? When can we call any pair of conductors separated by a dielectric media as a transmission line? Okay. So what is this all about? What is the difference, right? Let us discuss that. Okay. So first thing, can we call any pair of wires or any pair of conductors, right, separated by a dielectric as a transmission line? Okay, yes, you can call it, but the point is, you cannot, it is not required for us to deal them as a transmission line. Okay, so the transmission line theory comes into picture, or when we have to use this, whatever the transmission line theory or field theory which we call, right, into picture only when there is a transit time effect. Okay, so whenever there is a transit time effect coming into picture, then we have to deal the pair of wires that we take, the pair of wires separated by a dielectric medium system. The system, we have to deal it as a transmission line theory when we have transit time effect in our system. So what is this transmit time effect? Okay, what is this transit time effect? When will it come? Right? So let us discuss that. Okay, so first of all, what is transit time? Transit time, yeah. So transit time. So this is the effect by which, or this is the parameter which differentiates or which leads to the transmission line theory. So what is transit time effect? So whenever I have, okay, so a wire or a pair of cables like this. So this is my source and this is my load end. right? Now the signal is propagating from this a source to the load through this system. Okay, so the amount of time that it takes to travel, that the signal takes to travel from the source to the load. Okay, so the amount of time that it takes to travel, the time to travel from the source to the load is called as the transit time. Okay, is called as the transit time. Okay, so transit time here basically refers to the amount of time a signal takes to travel through the transmission line, or to travel from the source end to the load end of the transmission line. Okay, or through the pair of cables. Okay, right. Now at low frequencies, right, that is whenever the frequency is low. Okay, let us assume the frequency of supply voltage, which is 50 hertz, right? We know that. Okay, so at 50 hertz frequency, whenever the frequency is 50 hertz, okay, so the time period of this signal will be 1 by 50. So this is nothing but 20 milliseconds. Approximately we'll get 20 milliseconds. Okay, so the time period of the signal is 20 milliseconds, whereas the time it takes for the right, if the transit time, generally this will be in, right, microseconds or in nanoseconds. Generally not even microseconds, it is in nanoseconds. Okay, so if we have, right, comparably small distances, okay, if the length of this cable that we are considering is in meters, comparably, right, medium size uh, cables, so in those cases, right, the transit time that we have, okay, is very less. So it will be generally ranging from picoseconds to nanoseconds, right? 10 power minus 12 to 10 power minus 9. Okay, so, right, so at low frequencies, right, at low frequencies, we see that the time period of the signal, is much higher when compared to the transmit time, which we generally represented by tau. Okay, so tau is the transit time. Okay, so the time period of the signals is very high when compared to the transit time. Okay, so therefore, right, the time period is high means, okay, when we say 20 milliseconds, right, the half cycle is of 10 milliseconds. Each half cycle is of 10 milliseconds. So it is taking 10 milliseconds to do one exertion, one half cycle, to complete one half cycle. Okay, so within that, right, in just 0 point, let's say, right, if I have 1 nanosecond, okay, 1 nanosecond means 10 power minus 9 seconds. Let us say the transit time is 1 nanosecond. Okay, so, right, here, okay, so we can see that, right, the rate at which the signal is changing is very slow when compared to the time it takes for traveling through the transmission line, okay, or through the pair of cables. Okay, so the amount of the time it takes, the time period of the signal is very large when compared to the signal. So that means what we can say is the signal is changing very slowly when compared to the velocity of the signal that it is traveling. Okay, so it is traveling very fastly, so therefore absolutely no problem. Okay, so that is what happens is, because of all this, what we can conclude is, so the signal, because the signal change is very slow, so whatever the input you apply at the source end, right, in no time will go to the load, right, and whenever we are doing the analysis, the V naught that we take is, right, is absolutely corresponding to the input Vi that you have applied at that particular instant, and the output at each instant of time is, right, is the corresponding output for the input you have applied at that particular time, because in no time it is, right, transmission line doesn't do anything, it just have to transfer. Okay, so the signal is getting transferred in no time. Okay, so the V naught you getting here is nothing but whatever the Vi you have applied. Okay, so in just nanoseconds it is traveling. Okay, so there is no change, in the input, there is no right, the V naught and Vi are corresponding to each other. Okay, so there is no effect. In conclusion, I can say this: whatever the pair of cables that you are taking, they don't have effect on the, right, analysis of our systems or circuits. Okay, that is why in circuit theory we never consider the effect of wires or cables that you are connecting. Okay, because they don't have effect, right? Okay, right. Now this is the case one, scenario one, at low frequencies, right? Okay, when the time period of the signal is much high when compared to transit times. Okay, now, yeah, now let us consider the other scenario, right? Whenever we have very high frequencies, let's say the signal of 1 gigahertz, I'm just taking one frequency. So let us say I have a signal of 1 gigahertz, okay, right? So 1 gigahertz corresponds to 1 gigahertz frequency corresponds to, right, a time period of 10 power minus 9, which is nothing but 1 nanosecond. Okay, 1 nanosecond, right? Uh, okay, or this is one case, or even if the distance, the length of the cable, right? So one is this when the frequency is very high, or the other thing is, so let us say the length of the cable, is very large. Length of the cable is very large. When one of these two happens, okay, let us say that the transit time tau, the tau for 1 meter, for traveling of 1 meter, let us say it is 1 nanoseconds. So if I have 1 kilometer of wire, okay, 1 kilometer of wire, so then this will become 1 microseconds. Okay, so if I have 100 kilometers, okay, so this will become 100 microseconds, which is nothing but 0.01 millisecond. Okay, so if I have 1000 kilometers, okay, very long wire, so then this will become 1 millisecond. Understood? So as the length of the cable increases, right, the transit time is also becoming more and more. Okay, so when either of these two things happen, one, if the frequency of the signal is very high, okay, which is like this, okay, or when the length of the cable is large, okay, when the length of the cable is very large, let's say in kilometers. Okay, so in either of these two cases we can see that the time period of the signal is becoming comparable to the transit time. I'm not saying exactly equal, right, but it is coming in range, in comparison, right, in comparable, right, it is getting closer to the transit time. Okay, so the time period of the signal, right, and the transit time are close to each other or nearly, right, similar. Okay, so right, okay, so in this case, right, in this case, now if you see, right, yeah, so again I have a source to load, right, let us say that the signal is like this. Okay, the transmission line is like this. So the time period of the signal is, let us say, t is 1 nanoseconds. That means, right, in 0.5 nanoseconds it is, right, doing half cycle variation. So the signal change is changing very rapidly. Okay, let us say the transit time that we got here is 1 nanosecond. I'm considering 1 meter cable, let's say only of 1 meter. Okay, only of 1 meter, so 10, the tau is 1 nanosecond. Okay, so in that case we can see that, right, if the signal takes 1 nanoseconds to reach from here to here, right, but in meanwhile the input, okay, the signal that you are giving at the input of the transmission line, it has changed by one cycle. Okay, one full cycle. Okay, so what we mean to say is, right, okay, before the signal gets propagated from here to here, the input is changing very rapidly. So whatever the output you are getting at this end, right, whatever the delay in the delay, right, the delay, it was 1 nanosecond earlier, it is 1 nanosecond here also, it is not much difference, but the only thing is this delay is now becoming comparable to the, right, applied, becoming comparable to the rate at which the signal changes. Okay, so therefore, right, in this situation or in this scenario, what happens is the V naught that we get at the output, right, is not, okay, corresponding to whatever the input that is available at this point. Okay, so in this cases, the lines, the cables or the wires that we are using in the using for the transmission, they are also coming into picture and they are also playing a very crucial role. Okay, clear with this? Yeah. So the V naught that we get is not the V naught of this input. Okay, because right? It is taking some time. So by that time, the VI has changed, input has changed, input has gone to the next value. So if I take at any instant, okay, if I take any instant and I measure the voltage, input and output voltages, this V naught what you measured is not the V naught because of the input you have applied here. Okay, it is the V naught of the input you have applied some time back, isn't it? Okay, so there is no correspondence between the input voltage and the output voltage. Okay, so in this case, right? So here the delay in the delay, it is not increased, right? At low frequencies or at high frequencies, the delay in the cables is same. Only thing is at low frequencies, the delay is not at all comparable with the time period of the signal. So that's not a point at all. Okay, we don't consider the cables or wires into effect at all. Okay, whereas at high frequencies, or if the length of the cable is very large, right? In those cases, right, what happens is the delay becomes comparable to the uh, rate at which the signal changes. Okay, so therefore in those cases at high frequencies we need to consider the cables or the wires into account. Okay, so this effect by which, right, this overall effect of the cable by which it is impacting the analysis of the signals is what we call it as transit time effect. Okay, this is in short the transit time effect, and because of this transit time effect we cannot do the traditional analysis. Okay, we cannot neglect the wires or the cables. Okay, wires or the cables. So this theory, right, so this theory which is right, what we do the analysis considering the the cables or lines is what we call it as the transmission line theory. So these wires or cables also play an important role in the overall analysis of the circuit, overall analysis of the output. So therefore these also have to be considered, and this theory which is giving us these things are called as the transmission line theory. So we do the analysis of these wires or cables with the help of this transmission line theory or the distributed theory. Okay, so therefore whenever, so the simple point, okay, the point that I would like to conclude is, so whenever there is a signal of very high frequency, generally hundreds of megahertz or gigahertz, okay, or whenever the length of the cable is very large, let's say in kilometers, okay, in those cases we cannot apply or we cannot neglect, okay, we cannot neglect the wires or cables. Okay, so those also have a very important role to play. Okay, so in those cases the wires or cables are called as the transmission lines, and they also have to be analyzed, right, with the help of certain analysis techniques which we call it as the transmission line theory. Okay, so this is the thing, right? So the main reason for this is because the delay inside the cable is becoming comparable to that of the rate at which the input changes, the time period of the signal. Okay, so this is the thing, concept related to this. So in this next lectures we will be studying about how to do the analysis of the transmission lines. Okay, a pair of cables, right? So what is the circuit representation of this pair of cables? How do we calculate how do we approximate it as a circuit? What are the factors that affect the performance of this, right? Basically it has to transmit the signal. Okay, so whenever it is transmitting, right, how can we reduce, right, the effects that it produces like distortion or attenuation, delay, everything has to be reduced, right? So how can we make the transmission through the transmission line, right, perfect one, okay, a maximum possible one. Okay, so this is all what we are going to discuss in the upcoming lectures. So first we will be discussing about the types of transmission lines, the parameters of the transmission lines. Okay, then we will be calculating certain parameters like propagation constant, characteristic impedance, right? And from there on we will be seeing how we can make the transmission line an ideal one, that is a lossless one and a distortionless one. Okay, what are the things required for that, right? All these things will be discussed, and then we will be seeing how we can calculate the impedances of this transmission line, what are how we can use this transmission line as circuit elements, like inductance, capacitance, etc., etc. So all these things we'll be covering in the next lectures.